Thank you for the introduction. I'm Jakub, not Andrei. And I will be talking about deep reinforcement learning-based framework for cellular programming. So the key aspect in the analysis of the biological system is to understand the long-term behavior of the system. And we concentrated on the analysis of the gene regulatory network. And the model that we chosen was a probabilistic Boolean network. It premised the quantification of the influences and sensitivity of genes in their interactions. And from this, the dynamic of the probabilistic Boolean network is represented with the state transition graph. So, mathematically, the Boolean network is a graph consisting of binary valued nodes and some transition functions. And at each time step, we will choose one of the functions and update the graph accordingly, one gene at a time. Okay, so this creates the state transition graph. And we are interested in the attractors of this graph. And the interesting thing is that there is always some attractors. They can be single state, like the two blue ones in the bottom, or we can have multi-state attractor, like this dark blue one in the top. Yeah, so we are interested in controlling the network from one desirable state to another. So from one attracting state to the other. And the attractors represent the phenotype states that we can observe. So those are the states that appear in biology. Yeah, and when controlling the network, we want to perform perturbations, and we want to perform as few as possible, because they may be hard to perform, they are costly, so we want to minimize the amount. And to do that, we have to look at the whole dynamics of the STG, and not only the relational graph. So the state space grows exponentially. Okay. Yeah. So our idea was to model the state transition graph as Markov decision process. So mathematically, it's quadruple of state space, so state transition graph for us. Then action space. So we decided to allow our agent to perform 3 perturbations at a time. So an action is choosing 3 genes to perturb. We have state transition probability. So since it's probabilistic Boolean network, our actions are non-deterministic. So the same action can have different results depending of our luck. And obviously, we have the reward function. For us, it was big reward for getting to the target state and small punishment for each action taken. Yeah. So we can estimate the quality and value of each state by well-known equations. So obviously, this leads us to Bellman equations and their recursive version. And then we are doing Q-learning to train our network. But before that, we need to detect attractors. Yeah, so this is Q-learning, deep learning. Yeah. Oh, yeah. So we found out that detecting attractors is hard. It's exponentially hard. And we weren't able to do it for all our test cases. So we decided to create some statistical method for detecting attractors. It consisted of 2 steps. First, we did initial discovery, so simulating a few episodes of the environment. And then, as the training progressed, we were discovering more and more attractors, usually. Okay, so our results. So this is the comparison of our method of detecting attractor states versus the exact methods. It was tested mostly on the Bittner melanoma data set. And we can see that we were able to recover all the attracting states with 100% precision. And we were able to detect attractors even for the biggest network, PBN30, that we couldn't handle with the exact tools because it was too complex. And then the control of the network. So this table shows how many steps do we need to take between the source attractor and target attractor. So we can see that for small networks, we were close to the optimal strategy, but didn't quite reach this level. But for the big networks, we did it. We could find control for every pair of attractors, but the software that the optimal software could not solve this problem. Yeah, so it seems to be working pretty well. Yeah, and it was kind of rushed, but thank you for your attention.
Thank you. We have time for one quick question. Could you maybe tell something about the biological application again that you were trying to?
Yeah, sure. So the attractor states are the states that are observable in biology, that you can see in real cells. So controlling between them would be controlling between cell types. So using this method, if you apply it in the wet lab, you could change the cell fate and potentially like treat cancer or maybe create organs for transplants.
Okay,